Hello all, myself Phanikumar and I'm with Craig. We're going to talk about basically the possibility of extending the Caliptra subsystem itself to become a system level key management to deliver keys securely to the different hardware components within a system, right? So a quick recap, we have kind of like talked about similar thing in OCP EMEA, and we kind of shared our idea how this can be used and things like that. And there is a little bit of echo, right? Yeah. So as we have seen, LOCK is also doing similar things for NVMe storage devices. Like basically, the risk that we're trying to avoid or eliminate is basically today software components are really managing the keys, like basically whether generating or programming keys to the hardware components, right? Like DRAM controllers, PCIe controllers, or Mac controllers, any of these things. And it used to be the case for NVMe storage devices, which is kind of like being addressed by LOCK with KMB component. So we're trying to see how that KMB component and the LOCK can design to extend or enhance to kind of address similar problems with the remaining components within the system, right? So that's what is the solution proposal. Just a quick recap of OCP LOCK. It's very much focused towards NVMe SCD kind of devices. So it's kind of an optional component within a Caliptra subsystem, introducing key management block, which is kind of like owning the keys and delivering the keys to the crypto engines of storage device. No other component within the storage device can really look at these keys, right? So that way, like any mutable code will not have a risk of exposing those keys under any attack. So MCU is the one really controlling what to do, when to deliver, things like that. So similar approach we are trying to use in our proposal. So again, what it does, the KMB is the key component of LOCK, which is actually doing key protections and deliveries and derivations, anything, right? So it kind of like generates, stores keys, and securely distributes, and then it also has access control enforcements. So and then lifecycle management, like when to erase things, so all of these things, right? So that's what it is doing for the NVMe storage devices. The same concepts, how can we actually adapt for the platform level, right? So if you look at it, basically we can just reuse most of those features for the platform level as well. And like here, if you look at it, you have many components. They may not be within the a reach. So then we may have to kind of like maybe I will go to that next. But so what we're trying to enhance in the KMB is basically we will use a standard CKMS like SP800 130 standard based CKMS metadata and bindings, like what key needs to be given to the which particular component like DRAM or MagSec or whatever. And we are also trying to use a standard crypto like SP800 108 based KDFs, and a very lightweight crypto to encrypt keys that are basically being delivered to the independent components. So KMB will do a lightweight encryption and gives it to the hardware component. Hardware component can simply decrypt and start using those keys. Right?
Yeah. A key component of this is really that last bullet, right? Is secure key delivery to all hardware components. The issue ends up being that the most secure way to deliver something is going to be a point-to-point connection. So if we were to go to the next slide, so here's an example of a very large SoC, fictitious SoC, something similar to what we've built at Marvell many times. So you've got a lot of components, right? And all these DRAM controllers, they're going to need a key. You've got Ethernet MACs, you've got PCIe links, there's a crypto accelerator, there's a need to provision keys to all these things. And so we can generate these keys in Caliptra. We can have a KMS, KMB kind of a thing. The problem ends up being if we really, so you see how we have all these system fabrics, right? There's a mesh that's doing Qi, because these are ARM cores. There's I/O bridges to I/O buses that are non-coherent not in the same way the Qi bus is. The point is you have all these SoC fabrics, and they're going many places. And if you're going to put keys over them, it's a little bit harder to ensure that they're not going somewhere where they shouldn't be. So if you take another, so this is kind of highlighting the problem, right? Shared buses are going to pose a security risk, and if you want to do point-to-point buses, it's just not scalable. We can't do this. So the thinking is, can we create a virtual private bus? So one thing to highlight is that there's already an interconnect that's connecting all of the components together in order to deliver configuration information. This allows software to configure the chip, to set it up, to check telemetry data and all these kinds of things. It already exists, and it would be really nice to be able to just reuse it. And so our thinking was, let's reuse it by essentially having point-to-point keys. So what we do is we actually have the KMB talk to the APB bridge, and it's going to have an interconnect that goes all over the chip, goes to many devices. But what we do is we take the key that we're trying to get to these different hardware components, and we encrypt it. We encrypt the key, and then we send it over this shared interconnect. And it doesn't have to be APB. It could be AXI4. It could be a proprietary interconnect. It's not really relevant. The concept is we're essentially creating a virtual private bus by encrypting the transaction in such a way that only the receiving hardware component can decrypt it. And symmetric cryptography always has the key distribution problem, right? So that's what the single wire is. You see it's a serial wire. So we serially shift the key that you're going to use to decrypt your key blob. So you serially shift that. You only need to do that once. That's a bus encryption key. And now each of the hardware components has the bus encryption key that it can use to decrypt the key material that's being delivered to it. I don't know if there's anything else on this slide. Yeah. Here's an example of kind of like this unrolled, deployed at a SoC level, right? So you have your KMB, you have your serial wires going to all the destinations that need to have keys, and then you have your shared fabric that's containing all of the key material for all of the devices. But in each case, only the targeted entity is going to be capable of decrypting the key that's being transferred into it.
Just to add to this, basically, the KMBs can be kind of like put in multi-tied, so that like going back to the picture. So you can have multiple KMBs sitting closer to DRAMs and Ethernet switches or maybe PCIe switches, so that like KMB to KMB communication can happen in secure channel, logical secure channels, and from the nearby KMB to the actual controller, we can have dedicated channel going, so that way we can actually simplify the overall network within the SoC.
Yeah, you can have basically a hub where essentially you're releasing a key from one KMB to another KMB, and then that KMB distributed regionally. So instead of having every single entity, you might have hundreds and hundreds of entities. What you could do instead is have regions, where each region gives you the opportunity to have less hardware. Oh, what happened?
Doesn't go? Okay. So yeah, call for action is like basically we're trying to define this secure interconnect. So we would like to collaborate with the community, and we're also trying to see how this can be integrated into different systems. And so obviously this needs to be tested in some simulators and things like that. So any contributions over there?
Yeah, I think it's about throwing it out to the community. What other kinds of keys could it manage? We have DRAM keys in mind, MaxSec, but maybe there's things we're just not, we're not used to building in our normal SoCs.
Thank you.
Thank you.
Yo.
Yeah, I had a question. The key that gets transferred by the serial line, you said it's a. Is it one wire? Because it does need control signals, right? Like
You can do it with a single wire, believe it or not. We've done it. You can do everything with a single wire.
Okay.
So one way you can do it is what you do is you say the key is always 256 bits. The transfer will always be 256 bits, and it will always begin with a start bit. That start bit goes into a 257-bit register, and as soon as the device sees a 1, it clears the register, and then that first bit works its way down the serial chain until it hits bit 0. When it hits bit 0, it stops shifting.
okay,
So you can 2 wires is okay too, but you can do it with 1.
okay, yeah, thanks.
I just wanted to throw out one more complication. Even if you're not bringing symmetric keys into the device, the new version of XTS-AES, which is defined by the IEEE standard 1619, has set limits on how many bytes you should or absolutely cannot.
Yeah, I know about that. Yeah.
Okay, very
No, but for your question, yep.
Yeah.
No,
anyway,
I'm
I
agreeing,
just wanted to point that out, that you're
Yeah.
going to end up having to manage a lot of keys that simply don't fit over into the Caliptra and LOCK piece. So that'll be a complication for.
Well, but typically the 1619, what that added is it reduced, I think, to 2 to the 32 or 2 to the 40, but it's really the construction of how you're doing your tweak and you're breaking your memory into sectors. So I don't think you have to recycle keys. Once you get it set up, you should be good.
No, that's right. You do not want to recycle keys. The limits were recommendation of not more than 256 bytes, not more than a terabyte encrypted with one key, and absolutely no more than 256 bytes encrypted with one key.
That's true. You would need some keys.
Yeah, exactly. So you've got to manage.
But that
all
problem
these.
exists no matter how you provision those keys, how you get them to the hardware components.
That's true.
Yeah.
Okay, thanks.
Thank you.
Reed Hinkle with Synopsys. I'd just like to say this is a great idea. I think we have a lot of customers who could make great use of this, and we'd be proud to work with you guys on how we can make this real.
That'd be great. We're glad to have you.
Yeah.
Uh-oh.
Oh, hi. No, it's a good. Yeah, good stuff. I like this. If you guys would be willing, open to contribute to Caliptra, that'd be great. Question though about the threat model. Do we need more keys? Like, is there where's the motive? I'm not saying it's not there, but could you speak to the motivation of these buses are not safe for keys? Let's encrypt it.
For me, I think it's really about something we run into a lot, is that I've done a lot of things over the years that are secure. I know they're secure. I did it, so now I know I did it right. But is it provably secure? And when we're doing an audit and we're looking at this, and this bus goes everywhere, and it's going into all of these widgets all over the chip, and then one of those widgets maybe it has a debug mechanism. We have a lot of diagnostic things, and if it's going to our debug mechanism, you can trace everything that goes over that bus. So did everybody in every place that bus goes to, did they properly gate it? And you might be able to get a tool to prove it, I try to do just design by construction correct. You gotta look at it and it's right, and it can't be wrong because it's obviously right. And so that was kind of where we were coming from, was the thinking of, you know, if we put it over a shared fabric, you just have a little bit more extra work to prove that, you know, it's not going to leak. That was our motivation, and maybe we're overthinking it. It's definitely a possibility. Some of the SoCs we work on are 300 to 600 square millimeters, and there's a lot of people that are working on those kinds of chips that don't know everything about security, and that was kind of the, you know, just over designing maybe.
And another possibility is like basically the endpoint receiving the key could be running a mutable code, and shared bus content read by that mutable code could be a risk.
All right, we're up on time, guys, so we'll take more questions outside. But thanks very much, Greg, and thanks.
Damn it, Brian.
Thank you.
I'm with Jeff, though. Contribute it. Caliptra's waiting for it.